Alright, so sort of an interesting application of Lenz's law can be seen in this pipe here. So this pipe is actually, and you can sort of see on the top and bottom, it's got sort of a sticker on it. It says eddy current. But you can see on the top and the bottom, maybe I'll bring it a bit closer, but it's a copper tube. Okay, and the significance of this is that copper is not magnetic. Okay, so it's not ferromagnetic, it's not paramagnetic. Ferromagnetic means, of course, that it's an actual magnet itself, the magnets that we're familiar with in terms of bar magnets and fridge magnets and that sort of thing. Paramagnetic means that it would be like a paper clip. When we put it in the presence of a magnetic field, that it becomes magnetic. So if you attach a paper clip to a magnet, that means I can attach additional paper clips to that paper clip because it becomes magnetic. But if I take it away from the magnet, of course, it is no longer magnetic. There might be some residual magnetism, but it is not ferromagnetic. Now copper is neither, and this is the significance of it being a copper tube. Now what I have here is I have actually two sort of metal cylinders. So here's one. In fact, they both look identical. So I'm holding them here. They're the exact same color. They're the exact same shape. There's really no noticeable difference between the two of them. They're pretty much exactly the same. The real difference between them is that one is a magnet and one is not a magnet. Okay, so what we'll do is we'll drop the one that is not a magnet through the tube first, and it's not really going to be any big surprise here. We're just dropping a piece of metal through a metal tube, and it's just going to fall as you'd expect. So it falls, and there's really nothing sort of interesting there. Now I'm going to take the other magnet, okay, the other metal cylinder, which is a magnet, and I'm going to drop it through, and it's still going to fall through, but I mean, we can sort of count the number of seconds it takes. It falls very slowly. So let's go ahead and, so I'm going to drop that magnet through, and it's probably a good sort of maybe 2-3 seconds in there that it took to fall. So let's try that again. So it's going to be 1, 2, 3, yeah, so about pretty close to 3 seconds to fall. So obviously that there's something going on there, and obviously it has to do with the fact that it's a magnet. And I think the misunderstanding, the assumption that people are going to make, again, is that this is due to it, I guess, being attracted to the copper, because there's a misconception out there that all metals are magnetic, and so the magnet is just going to be attracted to the copper on this pipe. Now this is in fact not true. As I said earlier, copper is not magnetic. Okay, and just to prove this, I'm going to take this bar magnet here, and I see that there's absolutely no attraction towards the copper whatsoever by either the north or the south poles. So that's not it at all. It's not about a magnetic attraction. Okay, the magnet is not attracted to the copper tube. Instead, what's actually going on here is actually an application of Lenz's law. So as the magnet enters the copper tube, we're going to get a change in flux. Now that change in flux, of course, is going to actually induce a current inside the tube, okay? And the flux that's going to be induced will actually oppose the change in flux. Alright, so I just want to talk a bit more about what's actually going on as the magnet slides through the pipe. And in terms of the hand rules, can we explain why the magnet actually slows down? So the first thing I'm going to do is just determine which side of the magnet is the north pole and which side is the south pole. And I'm going to do that using this bar magnet. So I can see that it doesn't want to go in there at all. So there we go. So the bottom of the magnet, of course, is the south pole. The top is going to be the north pole. So let's just keep that in mind. Let's look at the copper pipe here. So remember, the top of the magnet is north, and now as I start to put that in the copper pipe, of course it's going to be, now the north pole is entering the pipe. And as we know from previous videos, we know that the flux is always going to go out of the north pole. So in this case, as the magnet falls through the copper pipe, the flux is going to be down and increasing. And as we know, Lenz's law then says that the induced flux in the copper pipe is going to then be up and increasing. And my fingers are then going to trace the induced current direction. And we know that copper is a conductor, so current can definitely flow through it. In fact, it's sort of like, if you think of this as a loop of wire, it's sort of like a loop, but we've got a whole bunch of loops all together the whole way down the copper pipe. So it's just like a lot of different sort of copper loops there. So current can definitely travel through and it can go around those loops, and it is still a closed circuit. That's okay. Okay. Now, as I said, the current's going to flow around this direction. Okay. Now, I'm just going to look at this now head on, and it's going to become a bit more clear what's going on when we look at it in this orientation. So remember, it's going around this way. The current is going around this way, the direction that my fingers are. Okay? So what I'm going to do now is I'm going to use, again, my right hand grip rule, but I'm going to apply it to a different situation, and I'm going to apply it to a situation where we have a copper wire, or any wire for that matter. And remember that if we have current flowing through a wire, my thumb points in the direction of the current flow, and my fingers are then going to trace out the direction of the magnetic field. Okay? So it's going to be a bit tricky in this case because we're using the right-hand grip rule for two different situations. Now the first is to indicate the direction of current flow through the copper pipe, which is this direction. But now I'm going to sort of look at, well, what's going on in terms of the magnetic field that's going to be produced as a result of that current. So I'm going to, okay, so it's going around this way. Now my thumb is going to point in the direction that the current flows, and my fingers are then going to indicate the direction of the magnetic field. And I'm just doing it for this top side of the wire. Now, of course, I would have to sort of change it because the current obviously is going to be flowing around in a circle, but I'm just doing it for just this top section of the wire, and I can see here that my fingers indicate the magnetic field lines, right, the direction of the magnetic field, and it's going to be up. Right, so just like changing this orientation, so I can see inside the copper tube, we're actually going to get magnetic field that is directed upwards. Okay? Now, that's actually going to oppose the magnetic field of the magnet. Remember that the north pole is the one that's on the bottom. And we know that the magnetic field lines go from north, so it's going to be downwards as it falls through the tube. And the induced current is going to produce a magnetic field that is directed upwards. So that means we're getting two opposing magnetic fields. Just like when I try to bring a north pole and a north pole together, right, with two different magnets, and they repel each other, the same thing is going to happen to this magnet as the magnet passes through the copper tube. So it's a bit more in depth, but if we sort of put the pieces together, we can see that as a result of Lenz's law, which then is going to induce a current in here, that current is then going to induce a magnetic field that's going to oppose this magnetic field, and ultimately that's what's going to slow the magnet down and cause it to fall more slowly.